everyone. My name is John Holt, and I'm your host for today's episode of Eyes on Earth, a podcast of the U.S. Geological Survey's Earth Resources Observation and Science Center. Managing water use in the face of competing interests and sometimes scarce availability is one of the most intensive of resource management tasks. Modern managers have come to rely increasingly on satellites like Landsat to help them do the job. Satellites can be especially powerful tools for tracking evapotranspiration, or ET. Here to talk with us about evapotranspiration is Gabriel Sinet, a research physical scientist at AROS. Gabriel, welcome to Eyes on Earth.
Thank you.
Can you tell us what evapotranspiration is and how it works?
Evapotranspiration is a process, it's a hydrologic process by which water returns back to the atmosphere.
Okay.
So it's basically plants withdrawing water from soil moisture and releasing it into the air. That's really like we sweat. Mm-hmm. That's another form of really saying sweat, a plant sweat or a landscape, a sweat of a landscape.
And the sweat in the landscape scenario, you're talking about evaporation, that's the landscape, right. And transpiration is the leaves.
That's correct.
Can you explain in simple terms how your model measures ET?
So, it goes back to really the process of ET or evapotranspiration. It's a sweat. So it's a water moving through a human body or through the plant system. Water moves, leaves our body. It gives us a cooling effect. So we call it evaporative cooling. The same thing when plants transpire water are taking energy. So the plant cools down. So a landscape or a crop field that transpires the most cools the most. So it's a cooler. It's like you put a thermometer and the kids in the armpit, and you see that you can sense the temperature of a body. Satellites, the same way, they look at the landscape. If it's a transpiring landscape, it becomes much cooler.
So you measure the temperature of the surface. It's almost like a laser thermometer for a charcoal grill.
That's correct. Laser thermometer just points at your head and forehead, and you measure that. Same thing, satellites look at the land surface, and the land surface is emitting energy. If it is a cooler surface, it doesn't emit as much energy.
I see. But this particular thermometer is 438 miles
That's
up.
Correct.
What can a satellite that high up tell us about how much water a farmer is putting on his cornfield?
Very good. So there's a good farmer, let's say, puts water, the right amount of water at the right time. So that landscape is going to be much cooler than a farmer maybe doesn't water the field very well at the right time. The difference between the two could be as high as 40 degrees Fahrenheit.
Really?
Yes.
From one field to the next?
It could be as high as that. So the one that's much cooler would be a good farmer, putting the right amount of water. But losing water is not a bad thing. So it depends. A farmer who's just losing a lot of water or applying a lot of water, most likely is going to get more yield. So water is really loss of water, or ET, is tied to plant biomass and yield.
So the healthier your crops are, the cooler they will.
That's correct.
Cool as a cucumber.
That's right.
And you get more cucumbers when you're cool.
That's right. Yeah. So now just by looking at the temperature of the landscape, that tells you how much water is being used.
Can you talk to us about how your model has been used to help deal with water rights issues in places like the Upper Klamath River Basin?
We were asked to monitor a management program, which they call it curtailment. It means they're curtailing the amount of water given to the farmers.
Sure.
So they said, well, because we want more water to stay in the river and to go to the lake, so we're going to put in place an order not to irrigate. So they put in place this program in 2013. So they asked us, can you check this?
Right.
And can you come up with an estimate of how much water is now available in the river? So we compared 2013 through 16, the ET of the farms, the evapotranspiration of the farms, right. The irrigated areas, and we compared it to years prior to that. Our analysis showed the target years, once the curtailment was put in place, the amount of ET was much lower than the base years. So this assured them, one, the curtailment has worked. People obeyed. But even with that, the first year was more obeyed than other years. Subsequent years was less. So the satellite data helps you monitor if even a program like this is working. And our end results showed because of that curtailment and lower ET, the river flow has increased into the lake.
So ultimately, you were able to sort of verify that this program was doing the job.
That's correct.
That's not the only place where this has been used, of course. President Trump signed legislation in 2019 that allowed the Bureau of Reclamation to oversee a water conservation plan along the Colorado River's lower basin, which is a huge area, right? Several states covered there. How is your ET work important to that plan?
We work both the Lower Colorado and the Upper Colorado, specifically the Lower Colorado River Basin. Researchers, managers contacted us to regenerate water use for the lower basin, irrigated area.
Similar to the Klamath Basin.
That's right. So before they had it compiled by hand using different methods, but now what they wanted is, well, can we use this approach? So they asked us to do this since in 1985, actually going back to 1975.
But you weren't doing this in 1975.
No.
It seems like you probably wouldn't have had your training at that point.
No, that's very true. That's a nice thing about the historical archive of Landsat.
Right.
Then you can go back and reprocess, and that's exactly the Lower Colorado River Basin interested in, is they asked us, can you go back and reprocess the historical water use so that they understand trends in water use?
Right. And do you have on the tip of your tongue how many hectares or how many acres you're talking about for that entire?
At least these are in several millions.
Several million.
Yeah, 2-3 millions.
2 or 3 million acres, right?
Acres of land, under irrigation.
I shudder to think how many ground stations you would need to do that job accurately.
Yeah, so that's a question. It's almost impossible to cover this with ground stations. It's just the cost is prohibitive to do this.
Well, let's move on to another example here. Can you talk at a large scale about how ET work is important in places like the Western United States and in Africa? Dry areas, basically, right?
So
dry.
Just ET is what they call sometimes the biggest part of the water budget. Much of the water globally, about 65 to 70% of that rain goes back as ET. It is not available for human consumption. Mm-hmm. So it's very important, especially in the West, drier land, how much water is used by ET, because that tells you not only its usefulness for crop production, but how much is available for human and industrial water use.
Right. So you can decide we can use this much or that much, and we'll still have enough.
That's
if you don't know what you have, you can't make those decisions.
That's right. It will help you plan. Well, maybe should we cut down irrigation by how much? How many hectares of land should we take out so that so much water will be available for other uses? It's the biggest component of the water budget, which is any water available as a form of rain, most of it will go back. If it is like, for example, evaporating from a lake, that's useless.
Right.
That's not available for you. Much of it is unavoidable loss. For example, shrublands and forests, and these are in areas we need to have forests, we need to have shrublands. What we're worried about is that fringe, that small amount of water that we have to balance. These are competing needs. The agriculture for growing foods, but also for industry and for domestic water supply. We can still play with that 5 to 10% number, which is very critical for domestic water supply.
But can you also work to capture more of this? I'm thinking of groundwater aquifer recharge. Is that something that this helps you do?
That's a very good point. So what you do is rainfall is your source, so you minimize unnecessary losses. Water, it can be captured by harvesting in the groundwater, just in time, put it in the ground in aquifers, or put it in reservoirs, deep reservoirs with less surface area so you don't lose it evaporating. If you just put it in small ponds everywhere, within a couple of months, you will lose it.
Right.
So being wise where to capture it by itself is very important. Right. You don't want to capture it in the desert, in a huge, expansive surface area where you're going to be losing it.
And again, knowing the ET rate gives you, 100 years ago, you could have built a check dam and sort of tried to capture this water, but knowing the ET rate helps you to decide, let's do that here and not there because we know the rate right here.
That's correct, yeah. Gotcha. So because ET is such an invisible, we don't know until we start understanding, and this is a science that has been growing in the last 50 years. Think about the rainfall, we have a way to measure it, You put a bucket, you can see how much rain. You say 1 inch, 2 inch rain. The same thing, river flow. It's a liquid. You can measure it. Both rain and river flow, they're liquid, and we know how to handle it. This is gas, and it's invisible to the eye. So satellite data is really helping us understand such an important component of the water budget.
Do you work much with other countries on their water use and management? Do you have some examples that you might share?
Yes, we do. ET can be used for drought monitoring purposes. Because really the response of the landscape, you may have a lot of rain, but if that rain comes in one day, it really doesn't say much about how crops and vegetation is growing. But ET tells you how vegetation is using the rain. So we use it for drought monitoring all around the world, actually, from much of Africa, Central America, and Afghanistan. So this is one of the important tools to monitor drought around the world.
We hope you come back for the next episode of Eyes on Earth. This podcast is a product of the U.S. Geological Survey, Department of Interior.
Thank you for having me.